Okay, welcome to the very first class of Don't Trust the Science. I wanted to do a few classes of which deal with topics that I don't find convincing in science, because I think there are some parts of science that we ought to doubt. And in fact, you ought to doubt all parts of science because that's the scientific method. You know, to improve, we doubt the previous theories and then we put them to the test, with real experiments, not with thought experiments, which is what Albert Einstein specialized in. And that's who we're going to deal with today. And in particular, I only really want to critique his theory of relativity, special relativity and general relativity, they're often called. I don't want to critique any of his work on the photoelectric effect, assuming that it was his work. And the photoelectric effect is a real effect that I actually had to study at university when I was studying chemistry. It's something that is at the very basis, it's at the basis of all quantum mechanics, really, this photoelectric effect. And it was what led to the development of quantum mechanics. And that's something which I actually am quite convinced about. But the theory of relativity, we are often told that the reason why it's incomprehensible, the reason why it sounds so bizarre and illogical, for example, space bending or time curving, the reason why it's incomprehensible to the vast majority of us is because we are too stupid to understand it. This is very often the case made if you don't understand the theory of relativity. And I think that 99.999% of people don't understand the theory of relativity. Well, you'll get told that you're too stupid. And I want you to remember that old story, I think it was Hans Christian Andersen who wrote it, about the two con men in the Emperor's New Clothes. Because those two guys told the king that the only people that can't see your clothes, they are too stupid and too incompetent. And so everybody pretended to see the clothes, and until finally a little boy pointed out the obvious, that the emperor was naked. So let's start at the beginning. And I'm not going to be able to explain precisely what the theory of relativity means because it is so, in my opinion, so illogical. It has so many internal inconsistencies. And so I won't be able to give you a good definition, sadly. But I do know that it involves bending space and bending time. And they're two things that I don't think can be bent in any way. You can bend a ruler, you can bend something solid, but you can't bend space or time, in my opinion. Now, Newton was obviously the first great man that managed to give us mathematical descriptions of the planets moving around the sun. And Newton had this idea of absolute space, because when the planets go round, you might ask, well, how do we know they're spinning and not everything else is spinning around us? For example, with the Earth, how do we know that the Earth isn't just still and everything else is spinning around us? And there was a big debate among people like George Berkeley, a famous philosopher, who said that something can't spin if it's in empty space and there's nothing else around it. It can't spin. But Newton said, no, you're incorrect, Berkeley. There's such a thing as absolute space. And so even a single ball, a single planet or ball in space can spin because it's spinning relative to absolute space. And this is an important idea because this is really where we're going to get to the nitty gritty of why I don't think the theory of relativity is convincing. Anyway, usually when I mention to people that I don't believe in Einstein, or I don't trust him, I don't think that that the theory of relativity is good science, usually they talk about two things. People will respond, what about the perihelion of Mercury, number one? And I discussed this with a student recently, and I did a bad job, and that's partly what inspired me to make this video, because I made some mistakes in that discussion, and I wanted to clear up my understanding and my opinion on this topic. So the perihelion of Mercury, you are often told that Einstein was the first man to mathematically show why Mercury wasn't following Newton's laws. This was a strange thing. I can't remember which French astronomer discovered this, but he realized that Mercury was not moving according to Newton's laws. And so we need something else to explain the movement of Mercury. Well, way back, long before Einstein wrote anything about the perihelion of Mercury, a guy called Paul Gerber in 1898 assumed a finite speed of gravity. In Newton's laws, the speed of gravity is infinite. There's an instantaneous gravitational force. And Paul Gerber said, well, maybe that's not correct. Perhaps let's assume that gravity has a speed, and it's a finite speed, it's not infinite, and that finite speed of gravity, let's assume that it's exactly the same as the speed of light. And working on that assumption, he managed to get a mathematical derivation of the perihelion of Mercury long before Einstein. And so if you think that the perihelion of Mercury must be explained by Einstein, you're wrong, because it was already explained in 1898 with this simple assumption, which, as far as I'm aware, matches Einstein's magnificent theory of relativity. Yeah, that the speed of gravity and the speed of light are equivalent. Now, Ernst Mach, someone who Einstein certainly read, yeah, Ernst Mach was someone who Einstein was very interested in. He wrote a book in 1907 where he specifically mentions Gerber's derivation for the perihelion of Mercury. It was in a book called The Science of Mechanics. And someone else later, who was a critic of Einstein, when Einstein brought out his 1915 work on Mercury's perihelion, well, he pointed out that Gerber's formula for the perihelion shift is mathematically identical to Einstein's formula for general relativity. And so immediately there were accusations of plagiarism. I mean, it seems to me that Einstein certainly had heard of Gerber because Ernst Mach wrote about Paul Gerber's mathematical description of the perihelion of Mercury. And so there are reasons to believe that he may have plagiarized that idea. Although you might argue that he added lots of extra information to it, and it became a lot more of a, perhaps it was more in detail that he explained this perihelion of Mercury, but it was mathematically identical to this earlier work by Paul Gerber. And so we can already see that relativity is certainly not necessary to explain Mercury's perihelion. All we need to do is assume that. We don't actually have to make all of these other assumptions about length contraction, time dilation. This is where things get thinner as they go faster. We don't need to actually have any ideas about any of that in order to explain Mercury's perihelion. All we need to do is make that assumption, okay? And so that is how I would respond to anybody who mentions the perihelion of Mercury, and they usually do. It's usually the first thing people speak about, and then they talk about the GPS, the Global Positioning System, and we'll talk about that in a second. But on this topic of plagiarism, you might ask, what role did Einstein's first wife, Mileva Maric, I think she's Serbian or something like that, but what role did his first wife play in the brilliant discovery of the photoelectric effect? Because she was working with him before 1905, before this effect was first published. She was actually working with him a lot. And certainly there are a lot of stories out there that maybe she played a very important role in that discovery. She was also a brilliant mathematician and physicist. In fact, she even did stuff with her hands, which I don't know if Einstein ever did, but she even built stuff, invented stuff, discovered stuff, because she built a certain machine. I'll tell you about that in a second, but one more thing. When Einstein did divorce Mileva, he actually gave her the proceeds, the money from the Nobel Prize for the discovery of the photoelectric effect. He gave the money to her. Now, maybe that was because he wanted her to look after his son, or maybe it was because he knew that she actually deserved that money. I'm not sure. But one other thing about this young lady, of course, this was a time when men could excel in science, but women, I imagine it was a lot harder. And when she invented, with another physicist, Paul Habich, she invented a small device for measuring small electric currents, and then Einstein, who worked in a patent office, patented that device. It was called the Einstein-Habich device. There was no mention of Mileva in the way it was patented. And when she was asked, I read this as an anecdote, maybe it's not correct, maybe it's just an anecdote from the internet, but I heard that when she was asked, why isn't your name on it, she replied, what for? We are both one stone, because Einstein means one stone. And so we're both the same. Why would I want to put my name on it? That just made me wonder about the photoelectric effect. Now, of course, this is all hearsay and gossip, and so who knows? I don't want to say that any of this is certainly the case. But I do wonder, I really do, how much of a role she played in the photoelectric effect, which is something I think is a wonderful discovery. It's nothing like relativity. Okay, so the second thing people often point out is the global positioning system, and they say with absolute faith and confidence that it's the theory of relativity that the global positioning system uses when it makes corrections. But, I mean, I'm going to tell you, I got this from a book. I'm obviously just an English teacher, by the way, so you shouldn't take my word for any of this. But I like reading books, and I read this book by an Irish engineer called Al Kelly, and he argues throughout the whole book that the global positioning system is based on the Sagnac effect. Yeah, something called the Sagnac effect. And, you know, while I'm on this topic, the Michelson-Morley interferometer experiment is nearly always brought up when people want to say the theory of relativity is certainly true. And the Michelson-Morley interferometer experiment was where they tried to find if light was slowed down in any particular direction because we were travelling through something which they called the ether. And the ether is like this absolute space, really. It's a background through which things travel, and so you can measure their speed relative to the background rather than relative to other objects, so that you can have some kind of preferred reference frame. And the Michelson-Morley interferometer experiment gave a null result. Yeah, they didn't record light travelling faster or slower in any direction. But it wasn't the only interferometer experiment. There were loads of different interferometer experiments, and a lot of them are described in this book. The Irish engineer is really funny. I like the guy. And one of the interferometers that was built by a French guy called Sagnac. And when Sagnac did this experiment, because you know, all the other scientists that I'm going to talk about, I'm not sure about Paul Gerber, he was a mathematician, but these guys all made things, they invented things, they did things, a little bit like Mileva, who did things. She made something. I can't remember any devices that Einstein made. Maybe I'm wrong, but all I remember from Einstein is thought experiments, which are not experiments. So Sagnac, what he did, he wanted to divide. He split a beam of light, yeah, into two directions, and then sent them in opposite directions around in a circle, but he used a very, very big long circle, yeah? And you can actually do this with fibre optic cables. You can actually make your own Sagnac interferometer. Just take the fibre optics and spin it round lots and lots and lots and lots of times. And when you fire light in two different directions, yeah, one going one way round the circle and one going the other way round the circle, when it's stationary, the two beams of light take exactly the same time to go round the circle, and so they leave at the same time and they arrive at the end at the same time. However, when you spin the whole apparatus, including the light source and the detector and the whole, when you spin all of that round, it doesn't actually give a null result. With rotation, you get a positive result. So that's showing you that you're measuring the light as having different speeds in different directions. In one direction, it seems to go faster than the speed of light, and in the other direction, it seems to go slower than the speed of light. Now, Sagnac believed he had proven the existence of a stationary ether with his device. That was what he believed. It's clearly giving, even though it's a very similar experiment to the Michelson-Morley experiment, and okay, it's not similar in the way they built the apparatus, but what I mean is, can you not see that this could be the Earth? And we're trying to show that when something is spinning, if you are on that spinning object, you will see the light going at different speeds in different directions because it's spinning. And this is actually a very logical explanation for all of this. And by the way, they use this technology in inertial guidance systems and Ring laser gyroscopes. And so the Sagnac interferometer is a very important device. But there's a very easy way of explaining what's going on here. And what it is if you look at the device from the laboratory, in other words, from a preferred reference frame, in other words, you might say from the center of the spinning disc, because the center of the spinning disc is not moving, whereas everything that's spinning is moving in relation to that center. And so if you look at it from the center of the disc, Well then, from that preferred reference frame, from the laboratory or the center of the device, light speed is actually constant. It's still going, both directions are going at the same speed, but because it's spinning, one beam of light has longer to go than the other beam of light, which has shorter to go, because the starting point is constantly moving towards one and moving away from the other. And so the light that you measure on the device is slower in the black direction, yeah, because it's got longer to go, yet faster in the red direction because it's got a shorter distance to travel. And so the measured velocity of the speed of light will be the speed of light plus the velocity of the disk for the red direction, or the speed of light minus the velocity of the disk for the black direction. And so it seems as though, relative to the laboratory, light speed is constant in both directions, but relative to the observer on the rotating disk, the light speed will be measured as different values in different directions. And so you might ask, and obviously I'm sure that the experts on the theory of relativity will explain how this is precisely what relativity predicts. Yeah, and okay, but I think we can predict this without believing in bending space and time. And I would also say it does sound as though we can't claim that the speed of light is a constant, independent of the velocity of the light source, because this shows us that we will measure different values for the speed of light. Although sure, from a preferred reference frame, the speed of light is constant, but from the position of the observer, we can't claim that the speed of light will always be measured as a constant, independent of the velocity of the light source. It seems to go against, yeah, this rotation and positive result, it seems to go against the Michael Morley null result. And certainly in this book, you do get the guy arguing that the speed of light is different, going west to east and east to west. That there is a difference, that you measure that difference, and we measured that difference when they had the atomic clocks on the planes, which we will speak about in a little bit. So yeah, they're the two main things which are brought up whenever somebody wants to convince me that Einstein is correct. And whenever I've read about both of them, I've become convinced that actually you don't need that to explain the perihelion of Mercury or the global positioning system. That the corrections that the global positioning system uses, they are these corrections. They're even called the Sagnac correction, in honor of the guy who actually experimented with rotating beams of light. Okay. Now, a few other points that I thought I'd mention that are just quite weird. E equals mc squared. Everybody knows that Einstein came up with that first, right? Wrong. Alinto di Pretto, yeah, my Italian viewers will be very pleased to hear this. It was an Italian, Alinto di Pretto, who first discovered or first claimed that energy equals mass times the speed of light squared. And he did it 2 years before Einstein. And it's just interesting that Michael Besso, who is mentioned in Einstein's 1905 paper on relativity, he was a friend of the di Pretto family. So there was a connection. I just find that interesting. You know, Einstein always denied that he had come across Gerber's perihelion of Mercury, and I find that hard to believe. And here he seems to know di Pretto, he had a link to di Pretto, he spent some time in Italy, and I do wonder whether that is another example of a great idea which Einstein took and then made his own. Okay, let's talk about some other guys, because it's not just me who finds Einstein's theory of relativity somewhat unconvincing and maybe even a trick. Louis Essam, yeah, this is a guy you can look up on Wikipedia very easily or anywhere else, and you can find his essay which deals with the theory of relativity. Louis Essam is a very famous scientist because he was known for the precise measurement of the speed of light. I think this was in the 50s or 60s. He precisely measured the speed of light. So he is someone who is working, again, doing real experiments in order to measure something real like the speed of light. He's not using thought experiments or anything like that. You might think that someone like that would be well behind Einstein's theory of relativity. And by the way, how did he measure precisely the speed of light? He used his own invention, which was, he was the first guy to invent the atomic clock. Yeah, atomic clocks work on they use radioactive cesium, I believe, and they measure how much radioactivity is fired off regularly from this substance, and that's how they work as a clock. Anyway, he was the inventor of this amazing device. What did he say about relativity? He was a lifelong critic. He said that relativity is a swindle, is a trick. He spoke about the planes, which took his own clocks, his inventions. Yeah, he spoke about those planes, and he basically came to the conclusion the atomic clocks on those planes weren't good enough to measure what they were supposed to measure. They weren't accurate enough, they weren't precise enough, and so that was a waste of time. And so he was quite critical of that particular experiment as well. Anyway, he thought that it was a trick, yeah, and that's someone who you would probably expect to be right behind Einstein's theory of relativity, because he was investigating the speed of light and time. Yeah, he was dealing with light speed and time, so all those topics that the theory of relativity deals with. Another very famous experimentalist, Ernest Rutherford. Yeah, this was the guy who was firing alpha particles at a very thin sheet of gold, and because they didn't just all go through, because some of them fired in random directions, he understood that the center of the atom was the nucleus, and the nucleus was much bigger than the other part of the atom, the electron. Well, it's much bigger than an electron. The nucleus is actually a much bigger part, and so he totally changed our understanding of atoms. And he's called the father of nuclear physics because he discovered the alpha particle, the beta particle, gamma rays. He discovered radioactive decay, basically, that same principle that Louis Essen used in the clock. He treated relativity as a joke. He was an experimentalist like Michael Faraday. He did experiments. He didn't do thought experiments, because thought experiments are not experiments. He did real experiments, and he said no more than 6 people understand the theory of relativity, so not a lot of people. And he said, and I'm certainly not one of them. Yeah, and so he made it clear that he wasn't someone, no, he was too stupid to understand the theory of relativity, just like Louis Essen was too stupid to understand as well. He called it a magnificent work of art, and I agree, that's exactly what it is. It's a work of art, it's a work of philosophy, you know, it's a work of thought experiments, but it's not a work of science. Lastly, Herbert Dingle. Yeah, a lot of people say that if you can't teach something to someone else, and everybody has failed who has tried to teach me this theory of relativity, everybody. If you can't teach something to somebody else, you don't actually understand it properly. Yeah, because you can't even explain it to somebody else. Now, Herbert Dingle spent his whole life teaching relativity. He was the top expert. He wrote textbooks for all the universities on relativity. Max Born, the great physicist, praised these textbooks, these relativity textbooks, and said how wonderful they were. Anyway, in 1955, he suddenly had a change of heart. And by the way, he even wrote for the Encyclopedia Britannica. He wrote their section on relativity. Well, in 1955, he suddenly had a change of heart, and he suddenly admitted, actually, I don't understand the theory of relativity. And from that moment, he became a lifelong critic. And he said relativity is self-contradictory, it's internally inconsistent, you know, it's illogical, and the twin paradox, where that thought experiment where twins are going out into space and then back again, he said that it's a total contradiction in terms, because each twin is younger than the other twin at the end of it. That's what he claimed. And he spent all of his life teaching relativity. And at the end of his life, that was the conclusion he came to. Relativity is incorrect, illogical. And so, yeah, that sums up my my treatment of the theory of relativity. I'm just not convinced. And please, I'm sure that everybody's going to be angry that I don't understand it, and there might even be some angry comments under the video. That's fine. I'm just too stupid to understand it, guys. That's all it is. So I'll see you in the next Don't Trust the Science episode.